Let's talk about object-oriented programming and why it's still important, even if you don't think it is, or think that OO is a very bad thing. While object-oriented programming might not be as on-trend as it once was, its impact on software development is still profound and lasting, and hard to argue against if you look at the evidence. That's our topic for today. Hi, I'm Dave Farley of Modern Software Engineering. If you came here looking for continuous delivery, don't worry, you're in the right place. We've recently changed the name of the channel. If you're new here though, do hit subscribe, and if you enjoyed the video today, hit like as well. So what are the principles and ideas behind object-oriented programming, and why do they still matter in today's world of software engineering? At its core, object-oriented programming is a programming paradigm based on objects. I guess that's pretty obvious from the name. But what defines an object? Fundamentally, objects combine data and behavior in one place. Here's some very simple code. Here's a car with some data that's specific to one particular car, like its current speed and how much fuel it has right now. But there's also some behavior, like accelerate, brake, or refuel, that will have an impact on that data. This is the idea of combining these two things together. If we accelerate, we increase speed and use more fuel, which is obvious from the code as well as our understanding of the world. Sure, there can be some downsides to this, and we'll get to some of those, but that's the basic idea here. Object orientation introduced the idea of classes, blueprints that define the structure and behavior of objects. These are kind of templates from which objects are created. So objects are instances, that is, unique versions of classes, each with its own data, but each instance has the same behavior as defined by the class. A key principle of object orientation is the idea of encapsulation, bundling code and data together so that you can hide complexity behind a hopefully simple interface. In our example, the complexity of how speed and fuel usage change as a result of acceleration is hidden from the user. All the user needs to understand to make use of this car is the idea of accelerate, brake, or refuel. This means that you can interact with an object without knowing or caring about how it works internally. At least that's the idea. Even this simple example, though, shows that it's a bit more complicated than that, really. For example, for this car, someone could cheat and simply change the speed directly. But I don't want to get too lost in OO language semantics and esoterica. So if this is new to you, trust me, there are ways to defend against things like that. My point here is that the basic ideas are useful and pretty simple, really. But that as ever, in practice, things can be and may be a bit more complicated than they look on the surface. This idea of encapsulation, though, is a really big deal, because before object orientation, we didn't really have much ability to do that kind of thing. This idea allows us to write software that can interact with often complex other pieces of software, and via software even with other complex pieces of hardware, without knowing or caring about how those things work. For example, modern operating systems can support complicated devices through polymorphism in the form of device drivers. These can access complex specialist services like sound, graphics, or even 3D objects in virtual reality, and almost anything else that we can think of, without caring about how any of these things work, but still allowing us to take full advantage of them in our own code. This simply wasn't possible to the same degree before object orientation. Let me pause there and say thank you to our sponsors. We're extremely fortunate to be sponsored by Equal Experts, Transfic, Tuple, and Honeycomb. Tuple builds software to make pair programming easier for people who work remotely. All of these companies, though, offer products and services that are extremely well aligned with the topics that we discuss here on the Modern Software Engineering channel every week. So if you're looking for excellence in continuous delivery software engineering, then please do click on the links in the description below and check out our sponsors. Object orientation changed the way we think about software. Here are 3 game-changing concepts that OO introduced. Abstraction. OO allows us to think in terms of higher levels of abstraction, concepts like account, order, or even car, rather than the nuts and bolts of individual variables or functions. This raises the level of clarity and focus in our code, adding a new, previously absent layer of abstraction, giving us more and more effective ways to think about and navigate our code bases. This is one reason why object orientation is popular for bigger, more complex code bases. Before OO, there were no lists or maps or sets. We didn't really think about things in those terms. Sure, the ideas and the data structures were known, but there were no implementations that we could reuse, other than our own usage-specific implementation. I remember a C program that I wrote that had 4 different versions of a linked list, 4 different implementations. That seems crazy now, but that's how most of the code that I'd seen up to that point was written. The next but allied idea here is polymorphism. This is the ability for objects of different classes to be treated as instances of the same class through some common interface. I can treat both a linked list and an array list as a list, or maybe even the more generic collection, allowing me to hide even more information in one part of the code from another. For example, a print function can work with many different kinds of printers, inkjet, laser, or virtual, all without needing to know anything about their differences. Polymorphism is the really big idea that allows us to encapsulate behavior by defining some ideally small common set of operations that we care about and expressing those in a way that allows us, from the perspective of a consumer of some code, to ignore the implementation details completely. And from the perspective of the creator of that code, we can focus more on just understanding how we want to build our lists, maps, print drivers, and essentially unlimited host of other things, and limit how they can be used to how we want them to be used by virtue of the design of our interface to that code. This encapsulation then works both ways. Our aim is to write our pieces in a way that they can be used in code that doesn't care how they work. I've used that phrase a lot so far, doesn't know or care how they work. But that is really the whole game here. Object orientation frees us and gives us a model that allows us to better abstract our designs, meaning that the key third idea in our list is modularity. By organizing code into classes and objects, object orientation makes it easier to navigate large complex systems. You can understand and work on smaller pieces without getting lost in the overall complexity of the system as a whole. Each part is more separate from every other part. These ideas fundamentally changed the world of programming and how we design and build software, whatever programming language or programming paradigm you choose to use now. Even if you don't write object-oriented style code every day, OOP's influence is everywhere. Let's look at a few examples of that. Graphical user interfaces are perhaps one of the strongest examples. Object orientation and graphical user interfaces were essentially invented together. GUIs were an OO idea. Object orientation made GUIs possible by abstracting elements like buttons, windows, text boxes, and menus into generic reusable components. The concept of device drivers had certainly been around for a while, but device drivers that abstracted access to more complex devices, like modern complex printer drivers or graphical drivers, are classic examples of polymorphism at work and arrived as GUIs demanded more complex access to more sophisticated devices. Your operating system doesn't need to know the details of your specific printer or graphics card for all of this to work. It simply calls the driver's methods via a polymorphic interface, and this delegates those calls to the printer-specific versions of the function that does know and care how your hardware works. Modern programming languages, even in non-object-oriented programming paradigms like functional programming, have borrowed ideas like encapsulation and modularity from object-oriented programming. OOP's legacy is so pervasive that we all tend to take its ideas for granted and assume that they're general programming concepts. But they didn't start out like this. They weren't general concepts then. Object orientation isn't without its challenges, though. Critics often point to overcomplication in the code. Poorly written object-oriented code can lead to bloated, hard-to-maintain code bases. This is certainly true. But then again, badly written procedural functional code is also bloated and hard to maintain. The reason that we see more badly written OO code is probably more because there is more notionally OO code written than anything else. So there's more bad OO code simply because there's more OO code. There's nothing inherent in OO that makes bad code. All code is more complex than it seems on the surface. Like many things in engineering, there are always trade-offs. Functional programming can support automatic concurrency more easily than stateful object-oriented code. But OO code has the advantages of supporting the broader organizing principles of abstraction and polymorphism that helps us to navigate and model our code bases at scale. There is seemingly something inherent to programmers that makes us write bad code sometimes, whatever form it takes. I've seen horrible code in pretty much every technology and programming language that I've ever used. Some of it was mine. So much so that I don't believe that the problem is really in the programming languages, but in the programmers. And maybe more probably in something profound in the nature of programming itself. It's always more complex than it looks on the surface. Many developers, though, misunderstand object-oriented programming concepts and end up creating horrible designs. As a long-time OO programmer, I think it's a reasonable, though perhaps also somewhat extreme statement to say that most programmers using OO languages don't write OO code. In a lot of code that I see, there's poor information hiding, little or no real abstraction, and no polymorphism except that provided by third-party libraries or OS services like GUI systems. Perhaps, though, the main thing that critics currently point to is competition from functional programming. Functional programming has certainly made big gains in popularity in recent years for its simplicity and clarity in some use cases. But functional programming languages for some reason haven't supplanted object-oriented languages in terms of common usage. The first non-hybrid functional language in 2024 was Elixir, and it was 35th in the list of popular languages. However, many of the criticisms laid at the door of OO are more about bad programming in general, rather than flaws in OO itself. As with any paradigm, the key is understanding how to apply it correctly, and programming is harder than it looks. Here's why I'd argue that OO remains relevant, though, important even today. Navigability. Large systems require clear structure. Object-oriented programming and design makes it easier to manage that complexity through its modular design approach. Adaptability. With object-oriented programming, you can make changes to one part of the system without breaking anything else. That's true of other programming paradigms too, but it's definitely true of object orientation. Bridging the gap between problem and code, I think this is a place where object-oriented design is particularly strong. It helps us to model real-world concepts more directly in the code, which makes it easier to reason about complex systems. A lot of OO code doesn't look like that, but as I've said, that's a problem with how we use it, not with the technology. This isn't about OO being good and functional programming being bad. Functional programming is a wonderful tool for the right things. But then so is OO. There is no perfect programming language, so there's not much point pretending that there is. Object-oriented programming has shaped the way that we build software. Even if it's no longer the hottest paradigm out there, the principles that it introduced, abstraction, modularity, and encapsulation, are essential tools to any developer's toolkit. If you want to dive deeper into object-oriented programming or other software engineering concepts, do check out our training courses that are linked in the description below. And don't forget to subscribe for more insights into continuous delivery and modern software engineering. Thank you very much for watching, and if you enjoy our content here on the Modern Software Engineering channel, please do consider supporting our work by joining our Patreon community. And to our existing Patreon members, I'd like to thank you once again for your ongoing support. It's very much appreciated, and we've got lots of exciting new things on the way. Thank you.